Bismillahirrahmanirrahim. Welcome back to Mathematical Methods of Physics. Today we will go over lecture number 31. Let's review what we have studied in the last lectures. In last 3 or 4 lectures, we studied series solutions of differential equations. So let me review the whole topic of series solutions. Power series, we studied, basically we reviewed the power series because you were already familiar with this series. Taylor series, then power series method to solve the differential equations. Then we studied ordinary and singular points of the differential equations. We studied series solution near ordinary points, series solution near singular points, especially the regular singular points. We haven't studied the series solution around irregular. Alright? Method of Frobenius was the technique to solve a differential equation by power series method, alright, near a singular point, near a regular singular point. Then we studied the Bessel's equation of order 0, formulation of second linearly independent solution, Bessel's equation and Bessel functions, Legendre's equation and Legendre's polynomial, properties of Legendre's polynomial, Hermite equation and Hermite's polynomials. So in the very last lecture, we studied the Legendre's and Hermite equations and their solutions as polynomials, and we found, I think, 5-6 polynomials of Legendre's and Hermite type. So this is the whole thing which we studied in the series solution of differential equations. Today we are starting our a new topic, which is the last topic of this course as well. This lecture and the next lecture will be spent on this new topic, and that will be it for the course. So today's outline is calculus of variations. So we will start this topic today, calculus of variations. We will go on to study Euler's equation, equivalent form of Euler's equations. So Euler equation or Euler formulation is a very important topic in calculus of variations. So we will be studying that, and we will be seeing the equivalent forms of this Euler equation. In some books you will see Euler-Lagrange equation. It's the same thing. So simply we call it Euler equation, but actually it is Euler's Lagrange equation. So what is calculus of variations? So let's start with today's lecture, calculus of variations. Motivation of this topic is calculus of variations deals with certain kinds of extremal problems in which expressions involving integrals are optimized. Optimized means minimized or maximized. A huge amount of problems in the calculus variations have their origins in physics, where one has to minimize the energy associated to the problem under consideration. Alright? These days, many problems of calculus of variations come from economics. Here, the main point is that the resources are restricted to us, so you might not see in the books these economic applications of the calculus of variations, but if you search it online or Google it, you will definitely see some. So we will focus on the general idea of calculus variations with few examples from mathematics, and that can be extended to physics and economics and other areas of interest. So let's define what a functional is. A real valued function f, whose domain is the set of real functions yx, is known as a functional, or a functional of a single independent variable. Thus, the domain of the definition of the functional is the set of admissible functions. Alright, so functional is a little different. It is a function basically, but the domain is a set of real functions here. In ordinary functions, the values of independent variables are numbers, whereas with functionals, the values of independent variables are functions. This is the main difference. If you are dealing with just a function, function can have numbers as its independent variables. But for functional, you must have functions. So functional act on functions and give you real value. Alright? So for example, the length L of a curve C, whose equation is y is equal to f of x. Now let's say a curve C is defined by this equation y is equal to f of x, passing through two given points x1, y1 and x2, y2. And the length of this curve is given by this one. It's a very well-known formula. from calculus, very basic formula. x1 to x2, it's not x square, x1 to x2, 1 plus y prime square dx. 1 plus y prime square dx. Now the length L of the curve passing through A and B depends on y of x. Of course, if I change this y of x, this L will change. All right. So then L is a function of independent variable y of x. It means L depends on y of x. Eventually, it depends on x as well. All right. But changing the function will change this length. All right, which is a function. So thus L is a function of y of x, which is x1 to x2, 1 plus y prime square dx. It's not x square, it's x2. So this defines a functional which associates a real number L uniquely to each yx, the independent function. Further, suppose we wish to determine the curve having shortest distance between the 2 points A and B, that is, curve with minimum length L. All right. Let's say we want to minimize this L, that because yx is not fixed, 2 points are fixed. So let's say we want to find the shortest distance. There can be many curves which can start from x1, y1 and stop at x2, y2. There can be many curves, right? So we want to find the shortest distance between these 2 points. So basically we can minimize this L, the length. This is the classical example of a variational problem in which we wish to determine the particular curve y is equal to y of x, which minimize the functional Lyx. So this is a very classical variational problem, calculus of variation problems. Hence the two conditions that y at x1 should be y1 and y at x2 should be y2, which are imposed on the curve, are known as end conditions of the problem. So these are the end conditions, right? It has to start from one point, stop at the other point. In between, whatever is going on, we don't matter. Only the thing is, it should be a shortest distance. It means the length should be minimized, all right, by fixing 2 points only. Thus, variational problems involves determination of maximum or minimum or stationary values of a functional. The term extremum is used to include maximum or minimum or stationary values. All right? So these are all called extremum. So let's discuss this variational problem in detail. Consider the general integral, which is a functional. So instead of, you see, this is a function of y prime. In general, it can be a function of y, it can be a function of x, y, and y prime on the right hand side. All right? So in general, I can write a function of x, y, and y prime from x1 to x2. Again, it's not x square, it's x2. A function yx which extremizes the above integral and satisfies the conditions yx1 is equal to y1 and yx2 is equal to y2 is known as an extremal or extremizing function of the functional I. A variational problem is to find such an extremal function y of x. All right? So because y is unknown here and I is a functional here, we want to minimize or maximize I here, extremize basically. All right? So we need to find yx such that this I is maximum or minimum, whatever we are interested in. All right? So that is basically a variational problem, a general variational problem of integral type. All right? All right, so now let's move on to discuss the Eulers equation, which is very important in calculus of variations. What is Eulers equation? Now, if you go back to the same functional I of y of x, which is x1 to x2, f of x, y prime dx, a necessary condition for this integral to attain an extreme value is that the extremizing function yx should satisfy this equation. All right? For all x between x1 and x2. So this equation, partial f by partial y minus d by dx of partial f by partial y prime is equal to 0. The second order differential equation is known as Euler-Lagrange equation, or simply Euler's equation for the above integral. This equation is known as Euler's equation for this integral. All right? So in general it is Euler-Lagrange equation, but simply we call it Euler's equation. The solution of Euler's equation are known as extremals or stationary functions of the functional. If we solve this one, All right, the solutions of this differential equation gives you the extremals of this integral. Extremals. So it means if you just solve this equation, you will get the extreme values here. You will get the maximum or minima, whatever you are looking for. Extremum for a functional can occur only. So extremum for a functional, this functional can occur only on extremals. All right, which are f, which are y of x. Now this is the general form of Euler's equation or Euler-Lagrange equation. So let's study some equivalent forms of this equation as well. Sometimes the equivalent forms are easier to consider or easier to use. All right, so we should know what are the equivalent forms as well. The proof of this Euler equation is not difficult. From here you can easily attain this point. In handouts, in lecture handouts, I will include the proof of this equation as well. All right, right now I'm just writing it here, but if you go through that proof, it's very easy. You really have no worries for that. Of course, at this level, it's MSc level, so I hope you should be able, if proof is written in front of you, I hope you should be able to understand. So let's not waste on proving this equation right now. Let's find the equivalent forms of the Euler equation, and I'll thoroughly go over it in this lecture. So if I differentiate f with respect to x, f is a function of x, y, and y prime. So if I take df by dx, I need chain rule. Partial f by partial x plus partial f by partial y times dy by dx. Similarly, partial f by partial y prime and dy prime by dx. All right. So here I can write this dy by dx as y prime and dy prime by dx as y double prime. So in simple notation, I wrote y prime and y double prime for d by dx, and remaining terms are as it is. Now consider d by dx of y prime partial f by partial y prime. You see here, this term, we are considering the second term. We want to differentiate it again with respect to x. So here I can use the product rule. Y prime as it is, d by dx of partial f by partial y prime. Similarly, partial f by partial y prime as it is, and the derivative of y prime is y double prime. All right. Subtracting the above equation from the second last, we obtain, if I subtract this and this, if I subtract these two, because this is the common factor, you see, the last term here and the last term here are common. So if I subtract, they will cancel out. All right, and I'll be left with these equations: partial f by partial x plus y prime partial f by partial y, and minus y prime d by dx of partial. So first two terms from here and the first term from here, they will remain. The last terms, they cancel out. So this is the expression I will get if I subtract this equation from this equation. So this implies that it is the d by dx of f minus y prime, because d by dx is one operator, so I can bring it outside, and f minus y prime df by dy prime, I can write it inside. All right, and I brought this partial f by partial x on the left side and remain. Here y prime is common. In these two terms, y prime is common. I brought this y prime outside, so you are left with partial f by partial y minus d by dx of partial f by partial y prime. Now this is that equation, the Euler equation, if you recall this one. Partial f by partial y minus d by dx of f by y prime here. This is exactly that Euler equation, and this is equal to 0, right? This is equal to 0 here. So if I replace 0 here, the right hand side will vanish. If the right hand side vanishes, you are left with only the left hand side. This is another form of equation. Now partial f by partial y prime is also a function of x, y, and y prime. Of course, if f depends on x, y, y prime, its derivatives in general should also depend on x, y, and y prime. So we called it phi. That partial f by partial y prime is equal to phi of x, y, y prime, just to simplify our things. If this is phi, then what is d by dx? I need d by dx of phi. You see, this is phi, right? What will be d by dx of phi? It will be partial phi by partial x, partial phi by partial y dy by dx, plus partial phi by partial y prime dy by prime by dx. It's again a chain rule. for a function of 3 variables. Alright, partial by partial x, this is not c, of course, this is x. X and c are together in the keyboard, so I guess it's a typing mistake. I hit c instead of x. Phi, I replace the value of phi. What is phi? Partial f by partial y prime. So phi is partial f by partial y prime. Here again phi is partial f by partial y prime. Phi is partial f by partial y prime. So I replace the value of phi in all these 3 terms and I got this expression. So substituting the above equation in Euler's equation we have. Now if I replace this expression in our Euler equation, I will have another form of the Euler equation, which is this. Alright, so these red ones, this red one is another form of the Euler equation, this red one is another form of the Euler equation. Alright, partial f by partial y minus second term of the Euler equation was d by dx of partial f by partial y prime. So I got this whole thing for partial f by partial y prime, so this is what I got. Alright, so this is another form of Euler-Lagrange equation. These red ones are Euler equivalent forms of Euler-Lagrange equations. Alright, so let's now discuss the general case of the integral. In here, we restricted ourselves to just first derivative here, x, y, y prime. But in general, your L, your functional I, can depend on any derivative of y. It can depend on y, y prime, y double prime, y triple prime, and so on. We cannot restrict it to one number, right? It can have more than one derivatives. So, in general, the necessary condition for occurrence of extremum of the general integral means your integral depends on x, y1, y2 up to y eta, and then y1 prime, y2 prime up to y eta prime, and so on. So in general, this function can depend on y, y prime, and so on, and it can also depend on more than one values of y. Like, not just one function, it is depending on more than one function. So let's say y1, y2 up to yn. Alright? So if it depends on y1 up to yn, then it should depend on their derivatives as well. Alright? So this is the general integral which we are considering here, that it depends on x, and then from y1 to y eta, it's not prime, then y1 prime to y eta prime dx. Involving eta functions, y1, y2 up to y eta, it's not a prime here, is given by the set of eta Euler's equation. Of course, if there are n, or if there are eta functions from 1 to eta, 1, 2, 3 up to eta, we are not using n, we used eta here. So if there are eta number of functions, then you should have eta number of Euler's equation, one for each y1, yi. Alright? So this will be it. Your Euler equation will have partial f by partial yi minus d by dx of partial f by partial yi prime, and I goes from 1 to eta. So one for each yi. For y1, you have one Euler equation. For y2, you have another. For y3, you have another. So you have eta Euler equations here, not just one Euler equation. Alright? Okay, so let's see the example of basically how to solve the variational problem. Find the shortest smooth plane curve joining two distinct points in the plane. So there are two distinct points, x1, y1 and x2, y2. Alright? And we need to find y is equal to fx, which gives you a curve C in xy plane passing through the points P1 and P2, given points. So it can be any curve. You see, this solid curve is any curve here, and I want to find that curve which gives you the shortest distance. Then the length L of a curve C is given by, we know that, we started off with this example. So your length of curve should be from x1 to x2. I'm copying and pasting, so it's, I'm carrying on this x square. I copied and pasted here, so it's again x square. It's x2, x sub 2. 1 plus y prime square and dx. The variational problem is to find the plane curve whose length is shortest, that is, to determine the function yx, to determine the function yx which minimizes the above functional. The condition for extrema is the Euler's equation. We know that these are equivalent forms. Let's go back here. We said finding yx which extremizes this integral is the same as solving this Eulers equation. So these are equivalent problems. So here what we are doing is we are solving this Eulers equation instead of minimizing the integral. So here f is 1 plus y prime square. So df by dy is 0. df by dy is 0, and why is that? Because there is no y explicitly here. It's y prime. So I can get the derivative with respect to y prime but not with respect to y. This is 0. And what is the partial derivative with respect to y prime? It is 1 over 2 square root of 1 plus y prime square and 2y prime. So 2 cancelled out, and your derivative of this with respect to y prime comes out to be y prime over 1 plus y prime square root is equal to 0. The derivative with respect to y was 0. So from here, now this is gone, so you have the derivative of this thing equal to 0. So how to get rid of this derivative? You can integrate. If I integrate, I will get a constant on the right hand side. Let's call it k. K is a constant. And now what is y prime? Y prime is constant times this square root of 1 plus y prime square. So I multiplied this on the right hand side, so I got this one. Alright, and from here, if you want to find the value of y prime explicitly, this is the implicit relation of y prime. Explicitly, you can take the square, combine this y prime terms, and then divide by the coefficient. You will get y prime is equal to k square over 1 minus k square square root. And now this whole thing is a constant because k is arbitrary constant. So k square over 1 minus k square square root is another arbitrary constant. So we can call it m. Alright. So now if I integrate, if y prime is m, then your y will be mx plus c. Integrating, we will get mx plus c, where c is the constant of integration. Thus the straight line joining 2 points is the curve with shortest length. And we should expect that, right, at the beginning in the plane, not in any other surface. If you are dealing with some other surface, straight line may not give you the shortest distance. But the problem is here it was a plane. On a plane, a curve joining the 2 points has to be a straight line to give you the shortest distance. If you are going like this, you will never get a shortest distance. You have to go straight to the second point. So we expected that at the beginning that this should come out to be a straight line, and you see we got yx to be our straight line, which minimizes the minimizes the distance or the length of the curve. All right. So that is the shortest length of the curve joining 2 points has to be a straight line, and in a plane. I'm not talking about any other surface. In a plane. All right, let's see another example of variational problem, shortest time problem. It's also called brachistochrone problem. Brachistochrone problem, shortest time problem. So what is the problem basically? Determine the plane curve down which a particle will slide without friction from a point A to B in the shortest time. So let's say a particle has to slide down along a curve C, right, from a point x1, y1 to a point x2, y2 in a shortest time, all right, without friction. So we want to find this curve. Now it's not about shortest distance, it's about shortest time. Assume the positive direction of y-axis is vertically downward, because we are finding the curve down, so we may take the y-axis as downward, just for our own convenience, all right. And let x1 is less than x2, means again it's for our own convenience that we are saying that A point lies on the left and B on the right. So you are moving like this, all right. Let pxy be the position, any position of the particle at any time t. It can be anywhere along this curve, all right. So let pxy be the position of the particle at any time t on the curve C. Since energy is conserved, the speed v of the particle sliding along any curve is given by, if you are sliding down any curve, then the velocity v of the particle is given by this. V is equal to 2g y minus y star, square root of that, where y star is y1 minus v1 square by 2g. Here g is the acceleration due to gravity, v1 is the initial speed. All right, so this came from the energy conservation, all right, If we conserve the energy is conserved. So from there we got this expression where y star is basically y1 minus v1 square by 2g. y1 is the initial point and v1 is the initial velocity. Choose the origin at A so that x1 is 0 and y1 is 0. Again, for our own convenience, see this point can be anywhere. We are not interested in the distance, we are interested in the time. So it doesn't matter if we are starting from origin. If we are starting from origin and going down, again time will not change. Alright, so it means I can start from the origin. For our own convenience, of course, x1 and y1 will become 0. So mathematically, it will be simplified automatically. So it means your v, which is the derivative of the distance as well, ds by dt, which is your velocity. Here, y star will become 0. The reason is y1 is 0. All right. So if y1 is 0, this term will become 0, and v1 is the initial velocity, and we are starting this from rest. Our particle starts from rest. It was standing at x1, y1, and it has to slide. All right, so we just left it at the point, and it started to move down the curve. All right, so it means initial velocity has to be equal to 0 as well. So this y star will become 0, so you will be left with just 2g and y. All right. Now if I integrate this velocity, I'll get the distance. Integrating this, we get the time taken by the particle moving under the gravity from a00 to bx2, y2. So here, because we are interested in time, not in the distance, so if I integrate it directly, I will get s, but what we did is, we separated the variables for t, and solved it for t instead of s, because we are interested in time here. Alright? We have this, ds by dt is equal to 2gy. So what I can do is, I can write ds by square root of 2gy is equal to dt. So now integrate. If you integrate, you will get t function of y of x is equal to integral of this whole thing, ds over 2gy, right? And x goes from 0, x1 is 0 to x is equal to x2. Alright, now where is s? We are integrating with respect to s. This s is the distance along the curve. S is the distance along the curve from here to here. Alright, so what we will do is, we will replace the formula by the element of the distance, which is 1 plus y prime square root dx. Right? This is the formula. It's again the element of the length curve is this. Without integration, this is ds. So you got from 0 to x2, ds is 1 plus y prime square root over 2gy square root dx. So this is your general, again, integral variational problem. So this is your f of x, f now. This function is your f, x, y, and y prime. So considering this, you can find the Euler-Lagrange equation and solve that. So what I can write is, I can write t of yx is equal to, so if I bring this constant outside and write the integral as 1 plus y prime square divided by square root of y dx, then my function here is f x y prime is 1 plus y prime square over y square root square. This is my f. So this is our variational problem, subject to conditions are the same, that y at x1 is equal to y1 and y at x2 is equal to y2. Alright, so this is our variational problem. So here f is this. So if I find partial f by partial y, this will be square root of y has negative 1 by 2 and y to the power 3 by 2. This will remain as it is, and this will become 2 times y to the power 3 by 2. All right. Similarly, partial f by partial y prime is equal to 1 over y prime by 2, and 2 cancels out, so you got y times 1 plus y prime square root. So this is what you got. All right. So therefore, the Eulers equation d by dx of, I'm using the equivalent form here, f minus y prime partial f by partial y prime. This is the first equivalent form which we studied, the red equations, equal to 0. This takes the form, then the Euler equation takes the form d by dx of f, which is 1 plus y prime square root by y prime. This is your f, and minus y prime and this thing, right? So minus y prime square, this becomes y prime square over y times 1 plus y prime square is equal to 0. So this is the form that Euler Lagrange equation takes after substituting the value of f. So if I integrate, so integration yields, this d by dx is gone, so I'm left with just 1 plus y prime square by y minus y prime square by y 1 plus y prime square is equal to constant, because we have integrated. Let me write it like this. All right. So now if I take the LCM, multiply here, cross multiply this whole thing, y and y prime, this y will be cancelled here, and you will be getting 1 plus y prime square minus y prime square is equal to k times square root of y and 1 plus y prime square. All right. So from here this cancels out, this is 0. So you got y times 1 plus y prime square is equal to 1 over k, and if you take the square here, you will get y times 1 plus y prime square is equal to 1 over k square, and call it k2, let's say. All right, call it k2, because it's a constant, another constant. So I can rewrite it, another constant, so I can write it k2. So this is what we got from the Euler Lagrange equation. All right, so this is the Euler equation which we got. From the Euler equation we got this thing. I did it on the board here. You see, here I wrote the Euler Lagrange equation directly and got this form directly, but I showed you the missing steps now. Now here, you see 1 plus y prime square. 1 plus sine square gives me nothing, 1 plus cosine square gives me nothing, 1 plus tan square or 1 plus cotangent square theta gives me something. So if I, for our convenience, because both y and y prime are coming here and y prime has square, it's a non-linear equation, it's very difficult to solve. So we are assuming that, let's say y prime has this form cotangent theta, where theta is a parameter. So theta is another variable that will be unknown to you. Then from the above equation we have y prime is cotangent square theta, so 1 plus cot square theta is cosecant square theta. Cosecant square theta, if I divide it here, k2 divided by cosecant square theta, this will be equal to sine square theta. So y is equal to k2 sine square theta, and I can write it as 1 minus cos 2 theta by 2. So k2 sine square theta is 1 minus cos 2 theta divided by 2. So this is what I got very easily by replacing y prime is equal to cot theta here. Now from here, I got the value of y in terms of theta. Let's see what is the value of x in terms of theta. What is dx? Dx is dy by y prime. Do you agree with that? What is dy by dx? dy by dx equal to y prime. So I can write dx is equal to dy by y prime. This is clearly dx. So now y is given to me. I can divide by y prime, dy and dy prime. So if I divide dy by y prime, I'll get this. From here I got dy, and y prime is just cot theta. So if you differentiate and divide by cot theta, this is what you will get. Again, I'm getting sine square theta. I can write it as 1 minus cos 2 theta. So this 2 will be cancelled out. So I got the value of dx. And now if I integrate this equation, I'll get x as well. By integrating, I will get k2 times 1 becomes theta, and minus cos 2 theta becomes sine 2 theta by 2. So this is what I got. By integrating, I got x is equal to k2 theta minus sine theta by 2, and another constant of integration, which is k3. It's another constant of integration. So x minus k3 is equal to this. I brought this k3 to the left. So x minus k3 is equal to k2 by 2, k2 by 2, 2 theta minus sine 2 theta. 2 theta minus sine 2 theta. Now I have conditions given to me, because I got x and y, and there are two unknown constants, k2 and k3. In these two equations, I have two unknown constants, so I need two conditions. If you remember, we have two conditions here, that y at 0 should be 0 and y at x2 should be y2. So I will use these two conditions. If x is 0, then y is 0. Alright, we have k3 is equal to 0. If x is 0, alright, so using this condition, y0 at x equal to 0, we obtain k3 equal to 0. It's very easy. You can replace y0 here and x0 here. You will come. You should have k3 equal to 0. It should not be difficult. So now, because in both the equations we have 2 theta and 2 theta, cos 2 theta and sine 2 theta. So if you want, and here it's again 2 theta as well. Alright, so wherever theta is coming, it's 2 theta. You see in all those equations, theta is 2 theta, theta 2 theta, 2 theta. So if 2 theta is the variable which is coming, or parameter which is coming, so I can, for simplicity, I can replace 2 theta by another angle which is phi. It's not necessary, but because your x and y are both functions of 2 theta, so I can call it 2 theta is equal to phi. So if in both these colored blue equations, if I replace 2 theta by phi, I will get x is equal to k2 by 2 phi minus sine phi. The x is k2 by 2 phi minus sine phi, and y is equal to k2 by 2 1 minus cos phi. Alright, so in here, these are totally determined by this parameter phi. So this is a parametric form of x and y. So we got the curve. This is the required curve that will give me the shortest time from moving from A to B. So the above equation represents a one parameter family of cycloids. This is a very well known equation. It's a cycloid. If you go back and open any calculus book, alright, and search for cycloids, you will see this is the parametric equation of the cycloid. Alright, with k2 by 2 as the radius of the rolling circle. Cycloid is given by the rolling circle. If you take one point on the circle and roll the circle, the curve traced by that moving point is the cycloid. Alright, so the radius of that moving circle is k by 2 here, and we have another condition left, because our second condition is y at x2 should be equal to y2. Y at x2 should be equal to y2. From there I can obtain the value of k2. Alright, again x2 and y2 are not fixed here, where x2, y2 are not given to us. So whatever we will get the value of k, that will again be represented in terms of x2, y2. But here I'm leaving this as k2 because k2 can be determined from the second equation. If you fix the second condition at 1, 1 or 2, 3 or whatever, then you will get this k2, value of k2 as well. Alright. So let's see how we got the value of k3 equal to 0 in that equation. Our y and x are given by these two equations respectively, 1 and 2. Alright. So x0 and y are 0. So if y is 0, implies from 1 we'll get k2 by 2 and 1 minus cos 2 theta equal to 0. So it means 1 minus cos 2 theta equal to 0. Because in general y is not equal to 0. Y is only 0 at x is equal to 0. So it means I cannot take k2 to be equal to 0. If k2 is 0, then y will become 0 for all the times. And we are not moving horizontally. We are going down. So y is not 0 for all the time. All right. So that's why this has to be equal to 0. Cos 0 is 1. All right. So 2 theta will be equal to 0. So theta is 0. So therefore 2 implies x is 0. 0 minus k3 equal to k2 by 2. And theta is 0. So 2 theta is 0 and sine 0 is 0. All right. So right hand side becomes 0. So minus k3 is equal to 0 implies k3 is equal to 0. So that's how I got the value of k3 from the parametric equations 1 and 2. So therefore our x becomes k2 by 2 phi minus sine phi, and y is equal to k2 by 2 1 minus cosine phi, where phi is 2 theta. All right. So this is the expression which we got at the end. So this is the curve, all right, which is, so this star, therefore this star is the required curve C along which the particle takes the minimum time to reach at final point, which is b x2 y2. All right. So if we use the condition that y at x2 is equal to y2, all right, this implies that x is x2 and y is y2, then star gives y, which is y2, k2 by 2 1 minus cos 2 theta cos phi, and x2 is equal to k2 by 2, and it's phi minus sine phi. So from here you can obtain the value of k2, all right, in terms of phi or x2 y2. All right. So we can eliminate, because y2 x2 are fixed, k2 is fixed, phi is not fixed here. So we can eliminate phi from these two equations to obtain the value of k2 in terms of x2 y2. Of course in terms of x2 y2, because the specific values of x2 and y2 are not given to us. So if I solve this for k2 and eliminate phi from here, I will obtain only x2 y2. So you don't have to do that here, because if x2 and y2 are fixed, you can do it easily. But how can we what you can do here is, you can from y2 is equal to k2 by 2, you can do this. This implies 1 minus cos phi is equal to 2y2 by k2. All right, and cos phi is 1 minus 2y2 by k2. All right, and now if cos phi is this, then sine phi is given by 1 minus cos square phi square root. All right, so 1 minus 2y2 by k2 square root. All right, and then x2 is equal to k2 by 2 times phi minus sine phi will be k2 by 2. The value of phi can be written as in terms of sine or cosine, whatever. Minus sine phi is given by 1 minus 4y2 square by k2 square plus 4y2 by k2. 1 and 1 are cancelled, so you got this thing. Alright, so here you got k2 by 2 5 minus 4 y2 by k2 is common, so you can take 4 as 2, and inside you will get y2 by k2 times 1 minus y2 by k2. Alright, or maybe if you further simplify you will get something. So you see here phi can be written as cosine inverse of something, of this thing. Cosine inverse of this thing is phi. So what you are getting is k2 in terms of x, x2 and y2. Alright, so the point here was that you got k2 in terms of x2 and y2. Alright, because of course x2 and y2 are not fixed here, they are not given. They are fixed but they are not given to us, so that's why it's not convenient to solve for x2 and y2 from these two equations, from these two. If the values of x2 and y2 are given, it might be easier to find k2 from here. So that's why we leave our answer till star, that x is k2 by 2 1 minus cosine phi, and y is equal to k2 by 2 phi minus sine phi, and we can just say that where k2 is determined or can be determined from the condition y at x2 is equal to y2. So from the second point I can obtain k2. So basically we were interested in the curve and we got the curve. Curve is a cycloid. Alright, so if you remember, cycloid was a curve which, if I take the circle with radius k2 by 2 here, in our case the radius k2 by 2, this radius is k2 by 2, and if I take any point and now roll the circle, if it is rolling without slipping or sliding, if it is rolling and the curve traced by this, point gives you, the curve traced by this point gives you the cycloid. Alright, so basically we got the cycloid, the curve that it will look like cycloid, so that gives you the minimum time, alright, from traveling from point A to point B. It didn't come out to be a straight line, you see. Alright, shortest distance, it was a straight line, but for shortest time it is not a straight line. Alright, if you move along a straight line, it may not give you the shortest time. So this was important in this example. Alright, so this is the equation for the shortest time between any 2 points A and B, and you were moving down along a curve, not horizontally. Alright, so this is the final answer, where k2 can be obtained from the second condition, as I have emphasized before as well. Alright, so important things in today's lecture were, first of all, this integral, that this integral is basically our main functional which needs to be minimized. It's a classical variational problem, so that's why we started with this integral. Alright, so any function y that extremizes this integral is our variational problem. Then we moved on to an example which was the shortest, second important thing was the Euler equation associated with this integral. Any y that extremizes this functional will be a solution of this Euler equation. So either solve this equation and get the answer, or directly minimize this problem. So it's easier to solve this differential equation. So we moved on to find some equivalent forms. In red one here, equivalent forms of the Euler-Lagrange equation. Then we wrote the Euler-Lagrange equations for the general case, and then we moved on to examples of a variational problem. First example was the shortest path problem, and we saw that the shortest path in a plane is given by a straight line. Alright, so this was a straight line. Then we moved on to the shortest time problem, and this did not come out to be a straight line. When we minimized the functional, first of all we created the integral. This is the integral we got, and after getting this integral, this is our f of x, y, y prime, and using this f we wrote the Euler-Lagrange equation, and solving the Euler-Lagrange equation we arrive at this solution, which is x is equal to k2 by 2 phi minus sin phi, y is equal to k2 by 2 1 minus cos phi. This is not 2 phi, this is cos phi. All right, we replaced 2 theta by phi, so this is cos phi. All right, so this is what we got. So we did 2 examples of the variational problems. So let's summarize what we studied in today's lecture. We started off with the definition of calculus of variations. What are our variational problems? All right. Then we defined our functional, and functional as an integral as well. And we defined the general case of the integral as well. Then we moved on to study the Euler-Lagrange equation, which is simply called Euler's equation. Then we studied equivalent forms of the Euler-Lagrange equations. 2 equivalent forms which were given in the red equations. And then we moved on to solve 2 variational problems. One was the shortest time problem, another was the shortest distance problem. All right. So next time I will continue with the same calculus of variations topic, and we will solve more examples. All right. We will find more variational examples, and we will solve them how to minimize or maximize whatever our interest is in those functionals. All right. So that is it for today's lecture. Thank you so much for being with me. Next lecture will be our last lecture, lecture number 32, and that will be it for the course. I'll see you in next lecture. Till then, Allah Hafiz and Assalamu Alaikum.